get started with Sebastian Raschka. He serves as Lead AI Educator for Lightning AI and is a former professor of statistics, which I told him, I said, oh, I love that you're a former professor of stats. So many people don't think about what goes in the black box. So my term for him for this conference is algorithms. Welcome, Sebastian.
Yeah, thank you for the kind introduction, Beverly. And yeah, thanks everyone for coming. I know it's maybe for some of you a bit early, so I appreciate the attendance. And yeah, I'm excited to talk about LLMs for everything and everyone. So I saw there are a lot of talks on LLMs later in this conference. So I thought it would make sense to give you a brief, let's say, overview of all the exciting things related to LLMs. So I was planning to talk a bit about using and customizing LLMs, some of the recent research directions, and also what's up next for LLMs, like where is research headed to, let's say, in the next couple of months or years, who knows? So some of the exciting, I would say, trends or things to look forward to. So yeah, just about me, Beverly basically summarized it already perfectly. I'm currently at Lightning AI. Many people probably know me also from my books on machine learning. I was previously at University of Wisconsin-Madison. 2 years ago, I joined Lightning, and then I had to decide. I was doing both, like whether I want to stay in academia or industry. And it was just a time where AI and LLMs picked up, and I found that pretty exciting. So I'm currently coding and working with LLMs at Lightning AI. So just to start this talk, maybe the big elephant in the room, why do we even care about LLMs in the first place? Of course, there's hype everywhere and a lot of news related to this, so it's already interesting to keep up with the news, which is always like this little dopamine hit if you see something exciting and read about it. But moreover, I think the main motivation is, whether it's, let's say, true or not, is that it promises us, also LLMs, large language models, promise us to make us more productive. So this is just like something that made the rounds on, let's say, social media a few days ago. I wouldn't maybe take this exact number too seriously, but in general, the idea is that LLMs are supposed to make us more productive, whether it's like writing emails faster or coding faster or more efficiently, for example. So that's the main promise essentially behind LLMs and why I would say most people care about them. So also to take a step back and to define what is an LLM even, like what is a large language model. So I was thinking, what is a large language model? We should probably start with a general concept or a definition. And it's a broad question. I was thinking about it. I think there is no precise term. It's essentially a large neural network. How large? It's really up to, I would say, the current month you're looking at LLMs. Currently, the smallest models, like Llama or Code Llama, are around 7 billion. There are a few smaller models, but I would say, 7 billion parameters is like on the small end. And it can go up to trillions of parameters. For example, I think NVIDIA or Alibaba had some trillion parameter models. GPT-4, no one knows exactly, but it's maybe also in that realm. So it's basically a large neural network, and it's often based on the so-called transformer architecture. I say often because it doesn't have to be based on the transformer architecture. I will also show you later some other large language models that are not based on the transformer architecture. So also for most people, I guess, if you think about the term large language model or LLM, you probably think about ChatGPT because that was essentially the web interface and model that really made it popular back in, I think it was like November 2022, where really the broader public got interested in LLMs. I mean, they have been around for a few years before that, but that is really, I would say, the turning point where people got really interested in that. So I wanted to just, for those who maybe have not looked into detail in how ChatGPT works, I wanted to briefly, as part of this definition, go over the things or steps to build something like ChatGPT. So usually for large language models, we have these 3 steps. So there's the pre-training stage, the supervised fine-tuning stage, and the alignment stage. So these are the 3 stages that go into a model like ChatGPT. And to start with a pre-training, it's essentially a stage where you pre-train a large language model on a large number of tokens. Again, there is no concrete, let's say, prescription for a number, but I would aim for something between billions and trillions of tokens, where a token is essentially a word, approximately a word in a text. And the task here, the pre-training task for most modern LLMs is to simply predict the next token in a text. And when we train such a model, people often refer to this as a foundation model. The reason is that it's like the foundation for work on top of it, like the fine-tuning and alignment. So it's essentially like the base model, if you want to say it like that. And just to highlight really, it's really just a next word prediction task where you just give it raw text and then given some context, it predicts the next word. And I really want to emphasize also that this is raw text, which means that we don't need any label information. So the label is essentially the next word we want to predict. And this is kind of very important and useful to make this architecture successful because people can access large amounts of data, let's say, online. Whether it's okay to use certain data sources or not, that's a different discussion. But from a technical perspective, at least it allows people to leverage large data sets without having to put in additional labor to label the data set, for example, which is usually the bottleneck in deep learning or machine learning, like getting labeled data. So the supervised fine-tuning stage then follows this pre-training stage where after this next token prediction, we have more next token prediction, but this time it's based on a specific dataset format where we usually have around 1 to 50,000 examples that are essentially labeled. It's still the next word prediction task, but now the task looks a little bit different. We have usually an instruction, and we have optionally an input and an output. So here, the difference to before is that we have a pair. So we have this input and the output, and this is usually something someone would have to generate. So you have an instruction, and then you usually have a person writing the desired response. And once you have such a data set, you can fine-tune the model to respond to certain instructions. It can be, translating text, summarizing text, doing some very basic math, or answering general knowledge questions, and so forth. And again, it's a next word prediction task, but the format requires more work. So this is a bit more labor intensive to generate such a data set, which is why these data sets are typically smaller. And I wanted to also emphasize before we really start going from word to word, here in this context, we provide the whole instruction to the model. That's what the model sees. And then the next word prediction task starts with this output. So it generates the output one token at a time. And there's a related format where we also can optionally provide some input. So this is optional. So for some examples, for some instructions, it makes sense to provide some additional input. For example, if we have something like, as an instruction, identify the odd one from the group, and then we have carrot, apple, banana, and grape. The task for the model is then to pick out the odd one. And you can also think about how this could generalize, for example, to classification tasks. So even like email spam classification, right? You can have multiple classes, you have documents, and you can categorize them and so forth. So beyond just thinking about instructions or general knowledge questions, these are very versatile models, essentially. And then the third step is the alignment step. So this is another fine-tuning step. It's usually using a different technique. And here, so it's essentially to align the large language model with human instructions. And for that, usually, not always, but usually people use a concept called reinforcement learning with human feedback, RLHF. And here on the right-hand side, I just wanted to show you what the advantage of it is. For example, on the y-axis, it's the win rate, let's say, against a baseline supervised fine-tuned model. And if we start out with a base model like GPT-3, which has only been pre-trained, you would get a performance like shown in this chart here. And then when we use prompting, prompting means that we ask the model multiple times and rephrase our instruction to get better results, then we usually get better outputs. So sometimes a certain instruction doesn't work as well as another, so sometimes rephrasing helps. So if we rephrase our outputs and always consider the best response, we are often or usually better than the base model. And then on top of it, if we now fine-tune our model with this step 2, the supervised fine-tuning, we get even better performance. So compared to a baseline model. And then when we add this additional step, this reinforcement learning with human feedback, in addition to the supervised fine-tuning, we usually get even better performance. So it's essentially a multi-stage process where we start with a base model, and then optionally we fine-tune it, and then optionally we align it, essentially. So that's like the common process for building a model like ChatGPT. If you're curious about how this works in detail, it's actually quite interesting. So I wanted to briefly go over this concept of RLHF because it's probably something that not most people do yet. And I think this might be something that, if we look at current open source models with some exceptions, what most people could do to their models to get even better performance out of their, let's say, open source models. So how this works is it's also a three-step process. So first, we start with sampling a prompt, so like an instruction, and then we have the humans writing the responses. So we are generating this data set, and this is usually time and labor intensive because we have to have people to write these responses. So it's usually not super trivial, but let's say we did this and we have a data set for that. We then do the supervised fine-tuning that I explained earlier and get a model from there. And then as the next step, we use this fine-tuned model, sample more prompts, and then we have humans rate these responses or rank them, essentially, like from 1, 2, 3, 4. We basically have multiple responses, let's say 4 responses, and we rank them from worst to best. And these rankings are then our labels. So it's another time and labor intensive step. But I would say it's a bit easier than writing a response because like rearranging the order of what is the worst, what's the best is slightly, I would say, easier than writing this response in the first place. So it's still time and labor intensive, but maybe less so as the previous step. And then once we have that data set, this ranking or the ranked responses, we can train a reward model. The reward model is essentially also a LLM, and often it's the same LLM that we used for the pre-training. So if we pre-trained a GPT-3 model, we fine-tuned this GPT-3 model, then this reward model would be another fine-tuned GPT-3 model usually. You can pick any model, but that's just how it's typically done for simplicity. So we have now 2 models. We have a supervised fine-tuned model, and we have this reward model here. So there's one more step, and that is using these 2 models. So it looks maybe a bit complicated, but essentially what we are doing here is we are now refining the supervised fine-tuned model using this reward model to provide new, let's say, rewards for new data points. So we have the supervised fine-tuned model, sample responses, have the reward model give it a score, how good is the response, and then update this model using something called proximal policy optimization, which is a certain form of reinforcement learning. So it's essentially improving the supervised fine-tuning model, going from the previous supervised fine-tuning to the alignment step, essentially. And once we have done that, so then we get something like ChatGPT, where we can then ask it questions, and it gives us pretty good responses. Okay, so this was essentially a lengthy introduction to LLMs and how we define the term LLMs. So I think when most people think of LLMs, these are the 3 stages that we usually associate with LLMs. There's a big question, probably from the audience, whether we even need RLHF. So you saw it's a quite complicated process, and do we actually even need to do all of this? Can we just maybe do the supervised fine-tuning and be done with that? And I will revisit this later. So there are some interesting works on that. I would say it's a future research direction, but I will keep this question open until the end of the talk. So a little cliffhanger here, and we will come back to that later. So I wanted to, in the main part of this talk, I wanted to talk about actually using large language models, like the different ways we use large language models. And I was thinking about all the different ways, or not all of them, but let's say the most important ones, how we interact with LLMs, or how different companies, individuals, researchers interact with LLMs. And I was thinking of 5 different ones. Maybe you can think of additional ways, and I would be happy to hear about that. Also, we can chat about that later on, and there will also be time for questions, I hope. So here I was just listing the 5 different ways I was coming up with, from simple prompting, like just interacting with a model like ChatGPT, to pre-training, fine-tuning, and prompting our own model, essentially. And I will go through them step by step. So for most users, me included, I use ChatGPT almost every day, like to fix my grammar or fix spelling errors. Sometimes when I'm not super energetic or excited about responding to an email, and I know what I want to respond, I usually write it in a more sloppy way, and then I say, ChatGPT, can you write this more nicely, for example? Things like that, so everyday tasks. Another one I was just recently working on was when I was working on a manuscript. I wanted to break this manuscript down into individual LaTeX files and then have one LaTeX file where I import all of them. And so I had something like include main chapter 1, and I didn't want to just copy and paste this all over for the 30 chapters, and I just asked ChatGPT, can you generate a list like that for me so I don't have to do it myself? And yeah, it worked perfectly fine. I could copy and paste this into my LaTeX document, and I was just thinking, this is usually what I used Python for. So usually when I had something like that, I was writing a bash script or a Python script, and now you can just put it into ChatGPT and it will come up with the right thing often, if the task is, let's say, simple enough. So it's just something I do every day where it makes my life a bit easier. Larger companies, for example, starting with this, is what companies nowadays start doing is pre-training and prompting in LLM. So not everyone would use something like ChatGPT, but some people want to train their own LLM on specific data, on specific domains even. So one example was a Bloomberg GPT. So here, Bloomberg, the company, for example, they created their own training data set. They used 50% general data and 50% finance-specific data. So here, they were pre-training their own large language model. So there's a lot of detail I realized in this table. But the takeaway is really that they used 50% finance data and 50% the general data that you would usually use. So in total, they had 3.6 trillion tokens for the pre-training. And the model that came out of it, it was then, for example, used to generate the so-called Bloomberg query language, which is, I think, proprietary database format that they use at Bloomberg, for example. So in this case, they were just preparing their own large language model for more specific tasks. And they were also using it to generate news headlines for finance-related articles. Of course, you could also use a general model for that, like ChatGPT, but according to the benchmarks, they could get better performance by training this model on finance data and then using this pre-trained model. So this would be a way, for example, some companies start using large language models by pre-training their own and then having it do specific tasks. Another step in between would be the fine-tuning stage that we talked about earlier. So the Bloomberg GPT model, it was essentially just pre-trained and then prompted to do these things. We can also insert this fine-tuning step. To pick one example, that would be CodeLlama. It's just a very recent model that came out 1 or 2 weeks ago. On the left-hand side, it's Llama 2, but I'm talking about the CodeLlama model. So here, what happened was Meta AI, the company, formerly Facebook, what they did is they trained this Llama 2 model, which is a model similar to GPT-3. It's just a bit larger. It's, I think, from 7 billion to 70 billion parameters. And they had their pre-training, so they pre-trained their own model. And then what they did is they further trained it on code-specific data. So, C++ code, JavaScript, Java, Python, and so forth. So it was just a general code database. And then they further, for one specific model, they further trained it only on Python code, like 100 billion tokens Python code. And then they had various fine-tuning stages and came out with these CodeLlama models. So here, this would be an example where a big company pre-trains their own large language model on general text. They didn't share what the text data was, by the way, but they pre-trained it on general text, then trained it further on code, fine-tuned it on code, and then had this model that you can then use to generate code. So from the paper, here's just one example of how you can use that model. And I was using this model the other day myself, and it works actually pretty well. So it's a very capable code model. So this would be an example of pre-training, fine-tuning, and then prompting. Another approach that many companies use is the so-called retrieval augmented generation. It's essentially like I call it always the vector database approach. And I don't want to go into too much detail here because the time I have is only so much, and I saw there are some other speakers talking about this later in this conference, so I will reserve the details for the other speakers to cover it in more detail. And I think this probably goes for all of these topics, so I'm focused here on the overview rather than the specific details, but in a nutshell, it's essentially that we take an external database or document, it could be, for example, a knowledge base, documentation of a specific tool, and then we break it down into smaller chunks, embed these chunks as a vector, a real valued vector, and have that in a database. And then when we use the model for a certain query, we get the responses in an embedded format, and we look for similar, for example, for similar embeddings, and then we generate the response by utilizing something that is already in the database. So this is only one particular implementation for that. There are multiple ways. Often people use two different models for that, for example. But the idea is that we use external data sources. So I would say the advantage here is that it's less free form what the model generates. If we have a customer and we want to insert in our response certain, let's say, citations or passages from a documentation, if a user asks about how to use a specific tool, or let's say our company's tool, then this is a way we can embed these documentation snippets in the response, for example. I wanted to also talk about open source, because that is something I think that is most interesting to most of you, because that's the way how you can use and customize your own natural language models. So we talked about ChatGPT. There's an API for that as well. But I think most people really care about training, customizing, and using their own natural language models. So I wanted to briefly, before I show you or talk a bit more about these different open source models, I wanted to just go over what the advantages and disadvantages are of using open source LLMs. So in my opinion, one big advantage of these open source LLMs is that we also get access to the log probabilities, so the outputs before the words, so the probability that this is the next token, or basically a probability score, or just any score for the outputs, which can be then useful for analyzing the confidence of that model, or ranking the responses if we have multiple responses and so forth. So we get more information than just the output text. We get the information before that, and if we generate multiple responses, we can get a better, let's say, feeling of, is this actually a confident response and so forth. And whatever we want to do with it, it depends on the application, but it gives us more options here, essentially. Also, for privacy and control, I think that's an important one. I know some companies, for example, they are simply not allowed to use ChatGPT for work because, people don't know what happens with the data. There could be proprietary data. It's not allowed to, for this data to even leave the premises in some cases. So if you run your own open source model, you have full control. The data never has to leave your computer, for example. And you have full control over it. You can change it, you can modify it, you can host it however you want. Another one is full customizability. So what I usually do, I do research and I want to change the models. I want to experiment with new techniques and so forth. And I need models where I have full access to the model and can make modifications to any part of it. Also, it's easier to implement deterministic behavior, like setting the temperature to 0 and to get reproducible results. So if you used ChatGPT before through the API, you can also set the temperature to 0, where the temperature is essentially like how random the response is. Usually when a user uses ChatGPT, you don't want to have deterministic behavior because then it might sometimes just generate all the same responses all over, and sometimes you want to try it multiple times. However, in ChatGPT, there doesn't seem to be a way to really get deterministic results. So that means even if you apply all the right settings, you always, or not always, but often get different responses. And if you think about building a system on top of this, like a crucial system that interacts with customers, sometimes this can be non-desirable because you want to test your system beforehand on certain prompts, and then sometimes it generates different outputs. Then it's like, wow, that is quite risky if I use that on my real customers, for example, if I can't really reliably test it. And here, this is a point, models don't change unless we want them to. So I would say this can be an advantage and a disadvantage. So if we have an open source model and we deploy that on our hardware, we have full control, and unless we want to, we never have to change that model. It is always the same. It produces, let's say, predictable or deterministic, deterministic results if we wanted to, but it also never changes. It can be a good thing. It can be a bad thing in terms of if we want to update it. We have to put additional work into it if we want to update it to a better model. So here, I would say one small advantage of something like ChatGPT is it gets upgraded over time, right? So there was ChatGPT based on GPT 3.5 and then GPT-4, and most people noticed that this model was performing better than the previous one. So we get these free upgrades, but then also, sometimes it's good. Sometimes we just don't want undesirable side effects. We want to have full control. So it's whatever you, depends on the application whether you see this as an advantage or disadvantage. One disadvantage of open source is that it requires access to hardware. So I would say it's gotten better, but it's still not super cheap to run open source models, especially the big ones. So this is still something to consider. And the other one is it requires some work, so you can't just go to a website, insert the prompt and get the response. You would have to often clone a GitHub repository, download the weights, and then go from there. So it's additional steps, some work. It's not much work, but some additional work. This was essentially the list I could come up with. You probably have more in mind. We can also chat about that more later, and I would be interested to hear what your additional thoughts on these are. So regarding open source models, there are a lot of options. So this is really a very, very small snapshot. So there are many, many more models out there currently even. So I would say, though, the big three categories are encoders, decoders, and encoder-decoders. So encoders are usually like something like the BERT family of models. Decoders is something like ChatGPT, GPT models, Falcon, and Llama. And then we have encoder-decoders like T5, BART, and so forth. So just briefly, what does it mean? What is an encoder? What is a decoder? And so forth. So if we briefly look at the original transformer architecture, which is shown here. So this was the architecture proposed in the Attention is All You Need paper in 2016, 17. And it's an encoder-decoder, which has two parts to it. So you have the left part, which encodes something, and the right one produces the output. And so typically the left part is considered the encoder, and nowadays it's usually the part that we use when we care about classification. So if you want to train, let's say, a model to classify spam versus non-spam email, or want to categorize newspaper articles or internal documents, usually you would opt for an encoder for that. So you have a model that reads in the input and then produces an embedding, and then you can usually train logistic regression classifier on top of the embeddings, for example, or a small multi-layer perceptron. And here the difference is really how that model is trained. Usually this uses a masked language modeling procedure where you mask random words instead of generating the next word in terms of the pre-training. And this usually produces slightly better embeddings for tasks like classification. And the decoder is what we talked about earlier, where we have this next token prediction task. So this is usually useful when we are generating text. So these are the GPT-type models. I also wanted to say open source is moving really, really fast. So there was this code llama model. It was like last week or 2 weeks ago. And actually there was a weekend, and then on that Monday there were already like 2 or 3 other open source models on top of that were fine-tuned and even better than that model. So it's just incredible how fast the open source community is moving. And this is actually very exciting. I think it's like a really exciting time to be in science, research, and open source, because you get to see all these cool, awesome developments. It can be a bit overwhelming, of course, to keep track of all of it, but it's still a very exciting time, I think. So next, fine-tuning and customizing large language models. So we talked about a bit about pre-training and prompting and open source, and I wanted to also talk briefly about the fine-tuning and prompting approach, where we don't worry about the pre-training, we just download a pre-trained model and then we fine-tune and prompt it. And this is usually something I would do myself. Like I would, let's say, consider myself as more like a tinkerer. I don't really pre-train models, that would be too expensive, but I like using pre-trained models, do research, develop new techniques, fine-tune them, see what's working better, and so forth. So the fine-tuning and prompting here. And for that, there are lots of options where you can download the weights because they are freely available. For example, Llama 2, Free Willy, Falcon, Vicuna, Pythia, Stable LM, Code Llama, all these models have free weights available online. We also have a GitHub repository that we call LitGPT, which is fully open source, fully free to use. And it's just like a collection, I would say, of code and scripts to load these models in the same context, in the same interface, and it's a very hackable, approachable collection of code that you can also use to customize these models easily. It's all in the same code base, and all these models can be loaded there. And this is what I personally use a lot, and I'm maybe a bit biased here because I'm a contributor to this, but yeah, I find this very useful. And I wanted to also then say, what is actually the advantage of fine-tuning? Before we speak of or talk more about fine-tuning, is it even worth fine-tuning a model versus just prompting a model? And I found a paper here. There are lots of different papers, but that had a very clear graphic where they used the GPT-3 model here as the baseline, and with prompting where you change, again, the input and consider the best response. And then they compared it on a specific task compared to a 11 billion parameter T5 model. So this model, the T5 model, I should have written this here, but it's about 10 to 20 times smaller than the GPT-3 model. GPT-3 has 175 billion parameters. This has 11 billion parameters. So you can see, you can actually fine-tune a smaller model to get better performance on a specific task than a general larger model here. And yeah, sure, some people might say, okay, GPT-3 is outdated, there's GPT-4 now, but the same relationship still holds if you put GPT-4 there, and then you fine-tune a different smaller model, for example, Llama, for example, on a specific task. I want to emphasize it's also task-specific. So GPT-3 and GPT-4 models are, of course, still useful as general models because these models are deployed and customers use them for different things. Some people use them for summarization, translating from one language into the other and so forth, where here the fine-tuned models are usually for a more specific task. So if you have a specific business problem that you want to solve, for example. So researchers, so I talked about, right now before about fine-tuning and then prompting. Some researchers just care about fine-tuning, also sometimes me included, and that is where we actually don't really use the model, we just want to develop more efficient techniques. So it's essentially interesting for those who are interested in new method development. And for that, again, open source models are crucial because you can't really do research on a closed model like ChatGPT. So there was a nice paper, an overview of all the different techniques for parameter efficient fine-tuning. It's not, let's say, comprehensive anymore. There are more techniques that came on top of that. There are, for example, Llama adapter, QLoRA, and so forth. But this is a nice overview of how active the research community is in terms of developing more efficient techniques for fine-tuning. It's a very nice overview. And just to give you an example here, so here they compared GPT-3 again, FD stands for fine-tuned, compared to LoRA, where LoRA stands for low rank adaptation, which is essentially a technique for more efficient fine-tuning. And you can see the GPT-3 model, it has 175 billion parameters compared to the GPT-3 LoRA fine-tuned one, where you only have to fine-tune 40 million parameters. So it's 5,000 fewer parameters that you have to fine-tune, and you get the same performance on these specific tasks, for example. So it's just the way we use the same model, but we don't have to update all the model parameters, which makes this much cheaper. So here is a comparison of the performance. And I was running some experiments where I was taking a Falcon 7B model, 7 billion parameter model, and I was trying some different techniques. I was implementing an adapter. So this is a Llama adapter method, a Llama adapter version 2, and then LoRA. And I just ran this on the 50,000 data points from the alpaca data set. And the 7 billion Falcon model finished in 1 hour when I was using adapter or LoRA. On the other hand, it took about 9 hours and 6 GPUs to fully fine-tune this model. And if I go back, you can see The performance is about the same if you fully fine-tune or you use a parameter-efficient technique on specific tasks compared to the full fine-tuning. However, you save a lot of time when you use this parameter-efficient fine-tuning, like really a lot of time. Okay, I must say, so I was using 6 GPUs here, and it's 9 hours. One of the reasons was also, even on the 6 GPUs, I was running out of memory, so I had to use DeepSpeed stage 2 with CPU offloading, so there was some transfer between the CPU and GPU in terms of the parameters, which made this a bit slower. So, but in a rough estimate here, full fine-tuning always takes more time than the parameter-efficient one because you simply have more parameters to update. And then also, I should have a slide here on the GPU requirements. So for the parameter-efficient versions, I was using 16 gigabyte RAM. It was an A100 GPU compared to the full fine-tuning where I needed all the 40 gigabytes on each of these cards to even fine-tune that model. And this is with LoRA. There's even a more efficient technique. I think it's a very crowded slide. I just did that last week, but there's another technique, QLoRA, which is quantized LoRa, and the only important part here is in the lower right. So by fine-tuning this model with QLoRA, I was able to get this even down to, it was about 13 gigabytes of RAM. So on 13 gigabytes of RAM, you can fine-tune a 7 billion parameter model, which is already great. And then, yeah, sure, there are larger models, 70 billion. You might need 4 GPUs for that, but it is getting, I would say, accessible. So these models are huge, but with these tricks, we can actually start using them like in smaller computers without having to have a big cluster. If you are interested in efficient fine-tuning, I wanted to highlight this really cool competition organized by NeurIPS, so the leading deep learning, machine learning conference in academia and industry. So it's a really big conference. Oh, I have only 5 minutes left. So, and I wanted to just highlight this because it's a really cool competition where it's about training a large language model for 1 day on 1 GPU. And researchers and practitioners come together to develop more efficient techniques. And I would say keep an eye on that competition. I think the results are due October 15th, and the workshop will be sometime December 16th, 17th. I would say if you're interested in efficient techniques, keep an eye on that. I think there will be a lot of efficient and exciting techniques coming out of this. Briefly about what's next on the horizon for LLMs. So I would say a big thing that is probably something we will see more of is the mixture of experts approach. So in brief, what that means is that we have sub-modules, or you can think of it as an ensemble of experts as a LLM. People basically say GPT-4 is a mixture of experts. No one knows 100% except the people at OpenAI who don't want to share this information, but people think GPT-4 is a mixture of expert model, which consists of smaller sub-modules, and these are then more specialized. And I think we will see more of this in the future, also for the open source models, because all the major open source models are still single models, and I think this is a trend we will see more in open source as well. I think we will see more multimodal models. So there are a few techniques like a Llama adapter, which can retrofit open source LLMs to also be multimodal, which means that it can also access images. So for example, you can have an image as input and some text, and it can then, let's say, describe what's in the image or something like that. We will also, I think, see more LLMs for different domains. So one I was picking out here is protein related, where a protein can be written as a sequence of amino acids, which are letters or characters. And I think we will also see more applications in biology. So there are already a few of them out there, but this is also something I think we will maybe see more often in the future. I also wanted to briefly highlight a few non-transformer large language models. So these are large language models that are large, but they don't use the transformer architecture. For example, there's the RWKV method, which is an RNN-based large language model. There is a hyena hierarchy, which is a convolutional large language model. And there's the retentive network that just came out recently. So all these three are different approaches to large language models that are not transformers. I haven't seen anyone else besides these works using those methods, so we will see whether they will be popular or not. But it's it's interesting to keep an eye on that. Yeah, do we need RLHF? Just briefly, there are alternatives out there. Here was one approach, relabeling data in hindsight by fixing the instructions after seeing the responses, and they just used supervised fine-tuning, found that this resulted in better performance than RLHF. I have 1 minute left, so I will just finish this up. So there's also direct policy optimization, and this is another alternative where it doesn't use reinforcement learning, it's directly optimizing based on the rewards. Again, I don't know if they will be popular. So these are papers that propose these methods. They look very promising, but I think most people still use or would use RLHF. It's just something to keep an eye on, and maybe this problem can be simply solved by these methods instead of this complicated RLHF. Yeah. So personally, things I'm excited about, I mean, related to LLMs, but also more in general. So just to wrap it up, I am always interested in new research. I write about new research papers. I have a little blog where I usually, go over the latest archive papers, summarize them, and talk about them. There's also LitGPT, which I'm involved in developing, this open source repository for loading and using and customizing large language models. And then, of course, this NeurIPS challenge that I mentioned before, I'm also working on this, and I feel this is like an exciting opportunity to develop more efficient methods. And yeah, with that, thanks everyone for attending. I think I'm just right on time. If you want to reach out, I will be here. Happy to chat. And yeah, thanks for being here. I hope it's going to be an awesome day, awesome conference, and yeah, talk to you later. If we have time for question, maybe we can have questions now or... Oh, one, okay.
One lucky person. Who wants to be the one lucky person?
But no pressure, I will be here, so we can also chat more later. There's one question, I think, yeah.
Yes. Oh, here we go. Excellent, you can take my mic.
I'm not real good at this LLM stuff, so forgive me if my understanding's off here, but when you talked about outperforming pre-trained models in a given specific domain, is there a typical size limit of how broad or narrow that domain can be to be able to outperform those large pre-trained models? So all documents in the classic literature of English language, or in the all court judgments in the USA, or something more specific like learning to code in Python, is it easy to outperform on some kind of larger, broader domain? Or do you have to have a fairly, when you talk about being able to train those T5 models, smaller models, and outperforming, when you talk about fine-tuning those T5 models, is it like on taking documents from within a company or some small domain and being able to outperform them? Is there kind of limits on that as you broaden the domain to being more general? Does that make sense?
Yeah, there's a bit of a feedback on these speakers, I think. So, but I think the main question was about, I think it was about whether how we approach this pre-training, whether it's worth it compared to customizing or fine-tuning models. And
how specific does the domain have to be able to get a benefit from it? Can it be a broad domain, or does it need...
I think the main consideration is, I think there is no comprehensive paper and study on that yet. And personally, like I mentioned, I'm not the person pre-training these models because it takes millions of dollars, usually, if you want to do it properly. But based on all the evidence, it's that so if you want the model to perform on a specific domain, that domain has to be more or less already in the pre-training data set. So the fine-tuning is really to refine the model to do a specific task, but the knowledge has to be already there in the pre-training stage, is the common perception. So this code llama model that I mentioned, that was pre-trained on language, general language, and then they further trained it on code before they fine-tuned it. So there is still this pre-training or training stage that is required for ingesting the knowledge. It's really a large corpus for ingesting, and the fine-tuning is really more for extracting or tailoring it so that it performs well on a specific task. You can, to some extent, also provide new knowledge over fine-tuning, but it is usually more like the pre-training stage, which has to contain the knowledge, if that makes sense. But also, I'm not aware of any comprehensive studies on that. It's more like a rule of thumb, I would say. But yeah, a good point, yeah. Yeah, all right.
Excellent.
Mm-hmm.